Good morning, everyone. My name is Harald Paganetti, and it is an honor for me to chair this Herman Sood Legacy Plenary Lecture. I have a personal relationship with Dr. Sood, as he was the first physician mentor in my career when I came to the MGH Radiation Oncology in 1998. He showed me the clinician's point of view as compared to the basic physicist's point of view, as I had previously worked in a basic physics lab. I learned a tremendous amount from him, and he was instrumental in my career trajectory and also in the career of many others in our field. He taught me to always put the patient first, no matter what the required effort, and to always focus on clinical translation of my research to make an immediate impact on patient care. Dr. Sood is a true giant in radiation therapy, particularly in proton radiation therapy. Proton therapy worldwide would not be where it is today without him. He led groundbreaking preclinical and clinical studies, but his main impact really came from his persistence in asking funding agencies to support research, as well as the establishment of a clinical proton machine in the early 1970s. Without his efforts, proton therapy might have never made it to radiation oncology mainstream. Herman Sood is no ordinary physician. His knowledge and, most importantly, interest in physics impressed me from day one. His philosophy always has been that he had to understand technology and challenge physicists in order to optimize treatment for his patients. It is thus fitting that this Herman Sood plenary lecture is on technology developments in radiation therapy, MR-guided radiation therapy. This is another emerging technology, such as the one Herman Sood pushed 50 years ago. Today's speaker is Professor Uwe Oelfke. He's the deputy head of the Division of Radiotherapy and Imaging and the head of the Joint Department of Physics at the Institute of Cancer Research and the Royal Marsden in London, UK. He has been working at the interface of imaging and therapy for decades and has significantly impacted medical physics research and clinical practice. And with that, I would like to first thank the donors that made this plenary lecture possible. I'm sure Herman Sood will enjoy this session. I know he's listening via Zoom, and with that, I hand it over to Uwe Oelfke.
One of the best and easiest ways to learn is to talk with somebody and ask a question, and never approach a question to someone as though you're trying to do anything other than learn why they have a particular opinion they've articulated. And you're not to get into a discussion to make a convert. What you want to do is to learn and not try to make anybody believe what you happen to believe, and be very certain that you don't take this belief business so seriously, because what you want to do is to base what you think or say on maximum extent possible on data or facts. And that's one thing I've always tried to make the young people understand, that you should be absolutely free in asking any question you want to anybody, because nobody is immune to taking questions, tough or otherwise. Certain things are being replaced by something that's better, because the young bucks coming along, they are taught. Do not think that what you are being taught is the best. It's the best that we know about, but you should be absolutely committed to making certain that down your career you make some contribution that advances the capability of delivering the dose to the target, or you find out what other people have thought about it doing, and you keep abreast, not just advancing, thinking that the only thing that counts is what you do, but what is being done by anybody in Tanzania or Harvard or any place else. If somebody has a better idea, you pay attention and get to it.
Thank you very much for this kind introduction, Harald. As the title says, I want to talk to you in the next about 45 minutes about new technical developments in radiation therapy with a special focus on MRI guide. Let me give you a brief overview what I want to discuss in the next 45 minutes. First, as an introduction, I want to talk about the rationale. Why do we need MRI-guided radiation therapy? What is the motivation for these technical developments? Second, we go into the challenges and solution for developing these hybrid devices which combine an MRI scanner with the modern dose delivery system or linear accelerator. Then there are specific problems which have to be solved, which come from the presence of a magnetic field in the patient and in the treatment room. So the measurement and the calculation of dose will be reviewed. And then we go more and more into clinical applications, look at the facilities, how the workflow is, and some clinical examples in this young discipline which have been proven how important MRI guidance can be. And I want to end my talk with some blue sky applications which we may see in the next 5 to 10 years in our clinic. Okay, let's start with the rationale. Why do we need MRI-guided radiotherapy? And in order to motivate this, I first review the concepts of intensity-modulated radiotherapy, the ability to shape our dose distributions according to the anatomy of the patient, and then how do we monitor this and ensure that what we have planned actually happens. This is the task of image-guided radiation therapy. Our standard devices for practicing IGRT are relying on X-ray sources, and so we'll, at the end of this chapter, discuss the problems and limitation of X-ray guided radiotherapy. All right, let's start with a typical clinical situation. We have obviously a tumor here in this patient, a macroscopic lesion, and if this is referred to radiotherapy, we have the general problem that we want to accurately hit an invisible tumor with an invisible beam of radiation. And how to shape these dose distributions around the tumor was very nicely demonstrated 30 years ago in a thesis by my admired colleague Thomas Bortfeld, where he demonstrated, like in this picture, with straight lines you can almost create any picture. So if you imagine, let's say in radiation, these are radiation beams, and you fire them into this patient, and the eyes here are the organs at wrist, and the tumor is somewhere here. So you can shape the dose in very complex forms. And this is demonstrated here. This is a patient who has a tumor which is wrapping around the optic nerve. Here are two tumor targets. There are 9 radiation beams with different radiation fields delivered from different directions. And with this intensity modulation reflected by these matrices of photon fluence, you can see that the dose is accumulating in the targets around the optic nerve of this eye, and so you can spare the organs at wrist and cover the tumor with dose. And this is called conformal avoidance of organs at wrist through intensity modulated radiation therapy. However, you also have to ensure that the patient really, at the time of the treatment, looks like you're expecting it. And our expectation comes from diagnostic images, and you can see here a lung tumor and on an MRI, and here a prostate, let's say on a planning CT. That is the expectation you have for the treatment derived from diagnostic images. However, if you don't have any possibility of looking into the patient while you're treating the patient or closely before you treat the patient, then it's very difficult to ensure that you deliver the anticipated dose distributions. So a primary aim of image-guided radiation therapy is to see what we have to treat at the time of the treatment. And if there is no image guidance, this is exactly what you see, nothing. If you switch image guidance on, then you see that there is breathing motion of this tumor in the lung on the left-hand side. You can see that the tumor is leaving the targeted ring which I drew. And also the CTs of the prostate tumor, according to the different filling status of the rectum, the anatomy is different every day. And this is the motivation for the development of image. And our current status of radiotherapy delivery devices, linear accelerators, are now equipped with imaging equipment. You see here two standard machines, a TrueBeam from Varian, a Versa HD from Elekta, and they have the standard configurations, a multi-leaf collimator for shaping the radiation fields, multiple photon and electron energies, flattening filter-free photon beams, and then for image guidance, a KV cone beam CT. So you see here an X-ray source and a flat panel detector, and if the gantry is rotating, you can acquire images, CT images of the patient directly prior to. Just to repeat, the standard configuration for X-ray guided radiation therapy, we have a kilovoltage X-ray source mounted to the gantry of a linac and an extra detector, and the imaging beam is mounted perpendicular to the treatment beam, where you have a second flat panel imager for detecting the transmitted radiation through the patient. Now, what are the problems with the standard technology for X-ray guided radiotherapy? First, we are well aware that X-rays have limited soft tissue contrast. The Compton effect and the photo effect mostly rely on electron clouds and the photon absorption cross sections, but the contrast you can achieve is really not that great, especially in soft tissues. It's very difficult and impossible to monitor organ motion during treatment because the technology of C-arm gantries is actually limiting the radiation speed to a minute per rotation. And then there's extra imaging dose to the patient some people may be concerned of, especially if you want to look into the patient for the whole treatment. So, and finally, we are very limited that we get physical information about the spatial anatomy of electron crowds. There are no signals really related to physiology, tissue function, or even tumor biology. As a demonstration of the much better soft tissue contrast, let's now look at an image of a prostate patient, and this is the image quality which we get from a standard cone beam CT. And if you now compare this image, the MRI image, which the image you have seen previously, it is immediately clear there's so much more information and soft tissue contrast in this image. For instance, you could look into the prostate, you can clearly identify the rectum. Now, why don't we have these devices? And this is the topic of the next section. How do you develop MRI linacs? What are the challenges and what solutions are available? The technical challenge of treatment-integrated MRI I will first discuss in a little bit more detail and then represent the commercially available solution. So what is the big technical problem to build an MR linac or a treatment-integrated MRI scanner? And it is the mutual electromagnetic interference between these two devices. First, the static magnetic field of an MRI disturbs the operation of the linear accelerator, and second, the moving metal components of the dose delivery system, like the multi-leaf collimator, disturb the image quality of the MRI, and we will briefly look at some aspects of both problems. Well, let's first discuss the challenge that the magnetic field of the MRI scanner is posing on the operation of the LINAC. Here you see the distribution of magnetic field lines in the room of a 1.5 Tesla MRI, and the thick black line here is indicating the 0.5 millitesla field strengths. Now, and if you look in the handbook of the MRI scanner, you already find a warning that the operation of certain electrical devices in this magnetic field is not allowed or should not be done. Magnetic fields may affect the function of devices in the vicinity of this magnet, and specifically linear accelerators, X-ray image intensifiers, gamma cameras get a warning that one should not do. And there are two major challenges coming from the impact of the magnetic field on the operation of the LINAC. First, the on-beam generation. You see here the electron gun of a LINAC. Here's the filament emitting the electrons. And of course, there's an extra Lorentz force of a moving electron beam. And this electron gun would not be able to emit this kind of beam into the waveguide, which is then used later to produce the Bremsstrahlungsphotons. Furthermore, the magnetic field will have an impact on the operation of electromagnetic motors, for instance, of the MLC. Just let's look at a simulation of the beam generation, for instance, in the waveguide. You see here that in this waveguide, electrons are entering the waveguide, there's no magnetic field strength, and this device is trimmed and calibrated in such a way that you have a sufficient output to be used for radiotherapy later. However, if you switch the magnetic field on, you can see in this simulation that the Lorentz force causes the trajectories of the electrons to be altered, and this has a tremendous effect. You see these electrons are basically reflected in these cavities, and there's almost no output leaving the waveguide. And second, let's look at one example of the impact of the operation of the LINAC on the MRI image quality. I think it's pretty clear on these images that you have these speckle and streak artifacts, which you can actually even see in K-space, and they are induced by eddy currents which are caused by moving magnetic objects like the gantry or the MLC in the magnetic field of the MRI. Now, what are the solutions of this mutual interference of LINAC and magnetic resonance scanner? First, you can think of a spatial separation of treatment and imaging device, or you use alternative radiation sources like cobalt, for instance, or the more sophisticated solution is optimize the electron guns, shielding all these part of the linear accelerators from the magnetic field as best as you can. And where you cannot shield it anymore, then you have to generate a low magnetic field zone at the location of the linear accelerators. And all these concepts have been used for the devices I will introduce in the next section. So let's look at the different strategies for devising new technology for MRI-guided radiation therapy. And I've listed here 4 approaches. First, the 2 prominent commercially available approaches, which I will discuss in more detail. These are cobalt sources and MR-Linacs designed by a company in the US called ViewRay. Then the MR and a rotating LINAC designed by Philips Intellector. The concept was developed in close collaboration with the University Medical Center in Utrecht. And then there are 2 other approaches, the rotating MR-Linac, which comes from the University of Edmonton, and then a more easy approach, the MRI on rails, where basically the MR is mounted on the ceiling and can rail from one room to the other, and there's a shared treatment couch between the Linac and the MRI scanner. That's an installation at the Prince Margaret Hospital in Toronto. Let's go through the various concepts and introduce them. First, you see here on the left-hand side the approach developed at the University Medical Center in Utrecht. There you have an MRI scanner whose coil design is modified such that the radiation beam can penetrate through the cryostat of the magnet into the patient, and this whole device can rotate around the patient. A more experimental approach is pursued at the University of Sydney by the group of Paul Keel, where you have a split magnet and you can orient the linear accelerator either parallel to the magnetic field lines or perpendicular. A similar concept with the split magnet and cobalt sources, but also with the MR Linac, with a conventional Linac, is realized by ViewRay, the Meridian system, and then an interesting experimental approach where actually the magnet and the Linac simultaneously rotate around the patient, as is indicated here. It's also a split magnet, as you can see, and the beam can be either inline or parallel with the magnetic field lines or perpendicular to the magnetic field lines. Let's start with the commercial solution of ViewRay, the Meridian system. This was actually the first pioneering system, and it went into clinical operation already in 2014. You see here an animation of how it works. So the patient goes into a split magnet, and you have actually 3 cobalt sources which can be used simultaneously. So you have 3 multi-leaf collimator, and while you're observing the patient anatomy, you can use this information to adapt your radiation field to the observed patient anatomy. The technical parameters of the system are like this. It is a low field split coil magnet of 0.35 Tesla. The field of view is 50 centimeters in a 70 centimeter bore, as indicated before. 3 cobalt sources and MLCs, which yield a combined dose rate of 6 gray per minute. And the MLC has 180 leaves per head, and the treatment field is almost 32 centimeters squared. What are the pros and cons of this system, of this cobalt system? Of course, it was very clever to have a radiation source which is not affected by the magnet. So one of the main problems, the integration of the linear accelerator with the MRI scanner, the most problematic aspects were simply avoided. Then also the lower magnetic field strength of 0.35 Tesla seems to have less impact on the electrons which are produced in radiation therapy within the patient and also within dosimeters. And we will talk about this in the third part of this presentation. On the other hand, you have to introduce the logistics of cobalt sources into your department again, and the low magnetic field may have some limitations for functional imaging in the future. However, this device was pioneered in the clinic at the University of Washington in St. Louis already in February 2014, and the biggest amount of data still comes from these machines. In this slide, I show you then the next upgrade of the cobalt machine, where actually a linear accelerator was integrated into this technology. The split magnet still is the same, but you see here is the linear accelerator. There's a double focused MLC. I will talk about this data a little bit later. And then there are various components belonging to the operation of the LINAC, which are shielded in these buckets. They are mounted on a gantry, and now you have an operational LINAC on a gantry, which is positioned such that it's operating within a split magnet. And these are the parameters of the machine. As I said before, the low field split coil of 0.35 Tesla stays the same. The field of view, a 6 MB flattening filter free linear accelerator, and a specialty is a double stacked MLC, which is double focused. And the first patient with this device was treated in Detroit in 2017. Now let's look at the second commercially available platform, the Unity system from Elekta and Philips. Conceptually, I already have explained it. I just briefly want to go through it. Here's the MRI scanner. You can see that the coils in the cryostat have been divided such there is a window so that the radiation beam can go through this cryostat and irradiate the patient. Then you have the multi-leaf collimator, the linear accelerator, and all this is mounted on a gantry which can rotate around the MRI scanner. And here you can see the operation of this device. There's the magnetron, the waveguide, the MLC mounted on the gantry, and you will see it rotate now, and then you can see the magnetic field which is used to do the imaging, and you see the radiation beam is delivered at the same time. A small video how this device was implemented in our department in London. You see the gantry and how the magnet is now pushed into the gantry ring, and as you can see it fits all nicely, and this was in 2016 in June. This is how the device looks like. The parameters are that it has a 7 MeV flattening filter free beam, and now the specialty is that it is a high field strength of 1.5 Tesla MRI, 70 centimeter bore opening. There are further parameters, and the first patient treated with this device was in May 2017. Now let's summarize the overview of the technology. The most prominent commercially available solutions are the ViewRay system with a lower field strength of 0.35 Tesla and the Elekta Unity system with 1.5 Tesla field strength. The radiation beam in both of these solutions is directed perpendicular to the magnetic field lines of the scanner. Next, we will now discuss what is the impact of the magnetic field on absorbed dose in the clinical setting. We have to consider that every electron which is set in motion in the patient or in an ionization chamber experience a Lorentz force, and this leads, for instance, to something we term the electron return effect. It also influences those measurements in magnetic fields, for instance the operation of ionization chambers, and of course we have to design new dose calculation engines which take care of the magnetic field. Let's start with the Lorentz force. You see here an electron beam which is coming from a source and traveling through vacuum. Now we switch magnetic force which goes perpendicular to the slide, and then you see that the electron beam is curved according to the Lorentz source, and exactly that is happening in a patient, as you see with this example. There's a photon beam entering a water phantom, there's an air gap, and then there's water again. And you can see the electrons which are produced in this water column here. They travel through air, but they don't have a built-up effect on this region. Instead, they are traveling within air and come back to the water column they were originating from, and this is called the electron return effect. And you have this, for instance, in patients where there are air cavities. This is termed the electron return. You can see this even on a more basic level, usually used for dose calculations, a point spread kernel. You know, you have a photon which is interacting, primary interactions in sets electron in motions, and this is the dose kernel from the electrons which were transporting the energy away from the primary interaction point if there is no magnetic field. But if you now switch on the magnetic field perpendicular to the plane of the slide, then you see that the Lorentz force is deforming these kernels, these electron kernels, more and more, and this is exactly what also happens in the patient. So we have to account for these effects. Naturally, that doesn't only happen in patients, but also for ionization chambers, where, for instance, the radiation beam can be directed perpendicular to the central axis of the ionization chamber of the cylinder or parallel, and you can then, for instance, irradiate with the linac. Here's a magnet which is put into the ionization chamber, and you have two configurations like this one, the perpendicular configuration and the parallel configuration, and the signal of your ionization chamber depends on this geometry. And on this slide you can see the different results. For instance, for the perpendicular approach, you see the electron tracks entering the ionization chamber, and you see that none of these tracks at a field strength of 1 Tesla is actually reaching the other wall and leaving the ionization chamber. So the path length is higher of these tracks, there are more of these tracks, and therefore the signal goes up with increasing field strength. But of course, if the field strength gets too high, then these electrons are leaving fast, and therefore you get this pattern. If you have the other orientation of the cylinder in parallel direction, you see that the electron tracks which are created have a shorter way before they leave the ionization chamber, and therefore you have this characteristic signal. And again, the higher the field strength is, the smaller the path length of the electrons in the chamber. But these effects are understood and can just be accounted for by consistent and well-regulated measurement protocols. Another surprise, and just to show you this effect, was the influence on air gaps. We are using these ionization chambers often within solid water phantoms, and here you can see that the radiation beam is coming from the top. There's an air gap on the upper side of the ionization chamber or on the lower side, and as you can see, depending on this small air gap, you get, for a field strength of 1.5 Tesla, a different signal from this ionization chamber. And therefore it is recommended, for instance, not to use solid water, but if you can, a water phantom. The last problem which you have to account for is really the transport in the dose calculation. You know, all these electrons, as indicated here, in a normal Monte Carlo simulation would now not travel anymore in straight lines as indicated here, but in curved lines. But this we can do with ultra-fast Monte Carlo dose calculations. Let's now summarize this short section about measurement and calculation of absorbed dose in magnetic fields. First, the dose calculation in magnetic fields has been solved by fast Monte Carlo simulations. And these new dose algorithms are then used in treatment planning programs, and they account for the Lorentz force and the electron return effect in patients, and actually that has been tested for a number of clinical indications. And finally, also for dose measurements, and not only relative measurements but also absolute measurements, this problem has been solved in magnetic fields through modified protocols, correction factors, and there was huge international effort to establish new dosimetry protocols in strong magnetic fields. Start this. Facility and workflow. This was our MR-Linac facility at the Royal Marsden in September 2016. Very soon thereafter we had our first beam. You can see here the logos ICR and Royal Marsden radiated on a film from the MR-Linac. You can see here the open gantry, the MRI scanner, the treatment couch. Next, we took the first images. It's not so easy to guess what this is, but I cannot ask you because it's not a live demonstration. So the first image was of a Snickers bar and an orange in November. And then finally, at about 2 years later, we have treated our first patient. You see the patient going into the device. We are taking the images. It's a prostate patient. The clinician, my colleague Alison Tree, is actually then modifying the contours of the prostate, how it's seen at this day. A new treatment plan is designed, and then after further verification, the patient is treated according to the anatomy we have just observed, with a very high image quality for MRI pictures. So let's look at this clinical workflow a little bit more systematically. The key part is the generation of the new treatment plan. The contouring has to be done in the moment by a clinician, although it's in the process for cases like the prostate that we transfer this task to a radiographer. Then there's plan optimization, checking of the plan, which is done by physics. Then plan acceptance, again by the clinician. The whole verification is done. And then there's the other arm of delivery, and all this is done under constant surveillance of the patient. For instance, we monitor the motion of the patient during this procedure. However, that has a price to be paid, and this is the treatment times. You can see that the time slots, and usually we have for radiotherapy in the order of 15 to 20 minutes, and now we are more in the order of 30 to 45 minutes. Because there are so many tasks to be done, but we are all optimistic that this will improve dramatically through more and more application of clever software modules. So far at our institute we have treated in the order of close to 80 patients with more of 1,000 fractions delivered. The majority, just because of simplicity, is prostate patients, almost half of all our patients, but then more complicated ones like head and neck, partial breast, oligometastasis, gynecology, bladder and rectum patients, and even more advanced applications in the prostate, like the prostate bed. Let's next move into more details of the clinical rationale and show some examples which hopefully convince you about the opportunities of improving the radiation therapy treatment for many clinical indications in radiotherapy. The problem MRI-guided radiation therapy can address superbly is the variation of the patient anatomy during the course of a treatment. And the course of a treatment lasts in the order usually between 4, 6, 7 weeks. There are some indications where it only uses 1 week. And the variation of the anatomy can occur from day to day or even during a treatment. And just one example is, for instance, a reaction we often want to have is a shrinkage of the tumor due to the radiation. And I show you here an example provided by Dr. Susan Lalondrelle of the Marsden, a gynecological tumor. And this is the size of the tumor at the beginning of the treatment and how it's reacting to the radiation, and it is shrinking. And now we have the opportunity, if we see this on a daily basis, we can adapt our radiation fields, we can make them smaller to account for this response, and therefore save the patient from extra dose which he would have received or she would have received if we have left the original big radiation field. Another example is what I just mentioned, that these changes occur even during the treatment, and this is indicated here by bladder filling. We have taken for prostate patients scans at the beginning of the treatment, and then we design a new treatment plan according to these images, and then for verification before we actually treat, another scan, and finally after the treatment when the patient is leaving. And this now shows you the size of the bladder averaged over 8 fractions. And you can see here that the mean is 142 cc. Then at the verification time, it's about 20 minutes later, it's already 236 cc. And then for the post-treatment image, the bladder has even filled more. And usually we cannot, or we do not account for this in the moment, but we will do in the future. Now let's go to specific patient examples. And this was a prostate cancer patient, and just to guide you through the anatomy, there is the prostate, which is the radiation target where we want the dose, and also the seminal vesicles. And then there are these structures around it which we want to save from radiation, the organs at risk. The rectum, the bowel, and usually the bladder. And the bladder is here. And now let's see what happened to this patient. There you see the original anatomy which we observed on the first day. And we usually what we do is we deliver the same plan. But now let's see what's happened. Every day of these 10 days the anatomy looks completely different. And if you just want to focus on the bowel, for instance, as a very sensitive organ at risk, which is indicated here by the arrows, you can see it is very small and far away from the target here. Then here it is closer, here it's further away, then it's closer again. And now we can individually spare this sensitive organ at risk from radiation individually on each day. So there's a good opportunity that we reduce the bowel toxicity for this patient by adapting the treatment plan on every day. The second example I want to show is from gynecology. You have here 2 radiation targets, a primary target indicated here and a lymph node, and you design a treatment plan. And you can see they are about 3 centimeters apart from each other. However, this distance is changing. And you can see this here where you have the radiation target and you see the lymph node, how it's changing the position on a daily basis. And again, by taking account of these variations, by designing a new treatment plan, the patient gets a much improved treatment. And the last example, again from gynecology, is this patient. You know, this patient is 20 years old and it had positive margins after surgery. And you can see in detail now that this target is very close to the bladder as indicated here, and also to the rectum. And you can specifically design a new target every day so that you spare these sensitive organs at risk from dose. And this is indicated on the next slide. You can see here fraction 1 of the treatment, let's say day 1. Your plan looks like this, shaping around the bladder and try to avoid the rectum. And you do the same thing on day 3, but the treatment plan looks quite different. So I hope these few examples have convinced you that there is quite a bit of mileage for various clinical applications in pursuing MRI-guided radiation therapy. In the last application on the clinical side, I want to discuss hypofractionation. As indicated before, prostate cancer and other cancers, the radiation treatment is given over a number of weeks. And here, this is a history of fractionation trials in our institute. You know, about 20 years ago, radiotherapy of the prostate was given over 7.5 weeks in 2 gray fractions. Now, the practice was actually changed in 20 fractions of 3 gray. This was done according to the CHIP trial of Professor Jernley at the Royal Marsden. And there's another trial led by our medical director, Nick Van Ass, where we now can treat prostate patients in 1 week. But where next? One can even be much more ambitious, and my colleague Dr. Alison Tree has just got funding, received funding for another trial where you go down to 2 fractions of treating a prostate cancer. That means a patient would be finished with his treatment after attending 2 sessions of radiotherapy instead of 7.5 weeks about 20 years ago. And why can we dare to do this? Because you can imagine the shorter the treatment course is, the more we have to concentrate radiation dose, higher radiation doses on fewer days. So it's very important that we have an extreme accuracy in delivering these high doses. So the trial will be like this. There's a group of patients which gets 5 fractions of stereotactic body radiation therapy, and the other one only 2 fractions. And then systematically the side effects and toxicity, and of course also the tumor control probability will be monitored. But this we can only dare if we are sure that these high doses are delivered with the utmost accuracy to the relevant anatomy, and that we can avoid the organs at risk like the bladder, the rectum and the bowel. So this is an enabling, MRI-guided radiotherapy is enabling these hypofractionated treatment regimes of extreme hypofractionation. That means less than 5 fractions, less than a week. Now finally, let's discuss 2 blue sky applications of MRI-guided radiation therapy. This is more from the physics point of view and also from the imaging point of view. The first one I want to briefly discuss is real-time adaptive radiation therapy. What about if we could monitor the patient completely every second of his treatment? And we can do this. We have the imaging device and the treatment device which are integrated with each other. They provide us with signals every second, and these online imaging data and dose delivery parameters can be used by fast software to create a patient model, reconstruct the delivered doses, and even have a quality assurance of our treatment while the patient is treated, because we can reconstruct or see immediately what dose has been delivered. And we use this information on the fly to re-optimize the treatment parameters for the next part of the treatment. So we have a feedback loop and we feed this information back to the treatment machine. And just here is a movie which is indicating this real-time adaptive therapy. This is a moving lung tumor here in the middle, followed by the radiation beam. And while we are treating with the different radiation fields, which you see here in the software platform, you see how the dose is reconstructed and built up on these images on the fly within milliseconds or seconds. This is just future vision, but many groups are working on this, and the achievement of this vision relies on the achievable image quality that we can actually dare such a thing. The other big opportunity, finally in my last slide, I also want to make the point that MRI-guided radiation therapy offers for us the opportunity to treat more biologically motivated targets and use more information. You see here at the left hand side the MRI image of a prostate patient I have shown now for a number of times, and this is only specific to the anatomy. These signals basically indicate the volumes and the extent of the tumor targets and the organs at risk. But MRI offers the opportunity, at least at high field strengths as 1.5 Tesla, to get a better picture, a more functional picture of the tumors and the organs at risk, which are spatially subdivided. This is challenging. You know, these functional MRI methods still have to be developed for these devices. Many groups are working on this, like diffusion-weighted imaging or hypoxia imaging. But then you have the opportunities through modeling to even have a finer treatment, a spatial resolution which is finer with different dose levels, often referred to as dose painting, or you can monitor the response of an individual patient and maybe de-escalate the dose in order to save organs at risk from toxicity. So this whole field of biological treatment adaptation is only enabled to these kind of devices. Well, that is the conclusion of my talk. I hope that you found it interesting, and now I'm happy to answer any questions you might have related to this talk. Thank you very much for listening.
Thank you, Uwe. This was a fantastic talk, really a great overview of MRI-guided treatment technology, but also how it is applied in the clinic. I would like to give Herman Sood the opportunity to ask the first question. I think we can have him connected via Zoom video. Let's see if that works. Yes.
Herman, can you look to you? Yes. You can ask your question now.
I would like to ask, what is the magnitude of the error when you're doing such fine estimation of the target and the target moves small amounts? And if you have very, very small margins around the defined target, it seems as though there's a non-negligible risk of the target moving out of your perceived volume as you're going through the course of treatment, unless you redo the whole treatment planning on a daily basis. And I know that's kind of an unrealistic question, but anyway.
No, it's not, Herman. Thanks for the question. Actually, we do a complete new treatment plan for each fraction on these new images. So this can be done fast, and we also are checking the plan. in the moment, we are a little bit conservative with our margins. For instance, when we started in prostate, the prostate volumes are a little bit smaller than the CT volumes in general, which we get for the prostate. And so we are a little bit, let's say, cautious in having very tight margins. Also, what we observe, and that these treatment plans are designed really to the individual contouring of the clinician. And at least my clinical physicists say, well, sometimes it looks like we're adapting more to the personal taste of the clinician for this target volume than to a very good consensus of all the clinicians in drawing these targets. What I just want to say, for instance, we had a huge number of delineation studies first for this new device because we want to have a completely MRI guided workflow, MR only. And so there were a huge number of developments in an international consortium. You know, we are in this Elector consortium where 7, 8 clinical sites are trying to come up with new delineation guidelines and so on. You're right. It's basically learning from the beginning and make sure that we don't run into risks which we underestimate.
Thank you.
Thank you, Dr. Sood. Thank you, Uwe. There are a couple of questions in the Q&A room. One is from anonymous attendee. It seems that the magnet TX configuration has certain advantages because the beam orientation is parallel to the magnetic field. Can you comment on this?
It's true. You would expect that, let's say, we don't consider the divergence of the beam, that the electron return effect is minimized. And the question is this really a huge advantage, or do we now have methods to get around it? I would be, I really want to see this new device also in the clinic. I think it's a great idea. And the more technology differences we have, the better it is for the field. I just don't know whether this device is clinical already anywhere. I would expect it would be at the university in Edmonton, but I'm not sure whether it is. Maybe the anonymous person who asked the question will know better.
The next question, of course, that's a question that we have to ask with Herman Sood being in the audience, and this being the Herman Sood plenary lecture. And the question is, are the physics limitations of combining MR with a LINAC also at play with proton radiotherapy?
I think the full potential of protons, as I think we have discussed for many times, still depends crucially on image guidance. And if one could do MRI guidance at a proton machine, I would be very happy if this can be facilitated. I know there were some approaches in the Netherlands, maybe also in Heidelberg, who wanted to study that. I'm not sure, for instance, at MGH, whether you have any plans to go into that direction. It would be very natural.
Yeah, I believe there are various groups also in Australia.
Paul Kiel.
Yeah. And others in Dresden, the Netherlands, and also MGH is involved a little bit with one of the vendors looking into proton MR, but there's certainly, I would say, more challenges than with an MR LINAC, with protons being charged.
I agree, but we live from conquering challenges, isn't it?
I agree. Question from Simon Powell. For real-time tracking, what internal landmarks would you use to get sufficient information in real time?
Well, for that, obviously, good imaging contrast is key. We have just done simulations. We have a first version, which is not a product, but we're working with a lector like University Medical Center in Utrecht too. So template tracking, fast template tracking, if the contrast is good enough, works fine. It's fast enough. Also, of course, it depends on the latency, your prediction algorithms. All this is in a moment explored. But it all depends. The better the image quality, the better the contrast, the easier the software you're developing has it to facilitate that. But it's a key component, absolutely.
Question by Reinhard Schulte. Thank you for your excellent overview. Would a fixed horizontal beam combined with a rotating upright patient simplify some of the technological challenges with MR image guidance?
That's a good question. I think it really depends whether you believe you can rotate the patient. Paul Keel's idea was that you can save quite a bit of cost and save the gantry. It's more a gut feeling. I think it's a lot of psychology. I probably wouldn't. My clinicians would be very hesitant to do this with the patient, but yeah, what should I say? I believe we should maximize patient comfort as best as we can in order to have a good clinical solution. Sorry?
It's all about compromises.
Yeah.
I think we have time for one more question by Ed Halperin. What are your thoughts about whether or not repetitive exposure of the tumor to the magnetic field will affect the RBE of the treatment beams?
It's a tricky question. First, with photons, we are lucky we don't have RBE only if you go to very low photon energies, because we have this 2 MeV per centimeter stopping power for electrons for a large range of MV beams. So far, at least the radiations for protons, that is of course different. So far, at least cell irradiations have not shown any difference in just cell survival experiments, as far as I know. These were very early data. I'm not aware of any experiments which really clearly indicate that there may be an effect of the magnetic field such that the biological damage is different. Not sure whether there recently have been indications. Maybe Harald, you know this field a little bit better than I do.
I haven't seen any indication or any data that there's an effect from the magnetic field. But yeah, I mean, of course there could be something there that we don't know of, but I haven't seen any data so far.
Yeah, I could not imagine on DNA level. It must be then on structural, biological structures and systems in the microscopic regime, but not on DNA directly.
So we are a little bit over time already. So, and we went through most of the questions. So thank you very much, Uwe, again, for this really outstanding talk. I really enjoyed it.
Thank you very much. You're so kind. You cannot imagine how painful it was to listen to myself for such a long time.
And also, I would like to take the opportunity to thank Herman Sood again for his tremendous impact in our field, and also not only as a clinician, but also the impact he had on technology and bringing the field forward on the technology side, which is not often happening with somebody trained as a clinician, but he really was instrumental to so many things we take for granted now in the clinic, also from a technology perspective, in particular proton therapy. So thank you very much. And with that, I would like to close the session. Thanks, everyone.
Thanks a lot.
Hello, this is Mommy. You want to do some Zoom recordings of 50 people next week? Yeah? You want to interview them all? They're all talking about radiation.